Greetings, welcome to lecture number 35 on basic circuit theory. I am Razavi. Today we will look at the step response of the series RLC circuit and see how we can formulate this response in different cases. We have an overdamped system or a critically damped system or an underdamped system. But before we go there, let's take a quick look at what we discussed last time to prepare us for this type of analysis. We saw that if we have a general linear second order differential equation with this side a constant that is not zero, so that indicates that there is some sort of input, then we notice that at time infinity the value of y should be given by this constant divided by this coefficient. And the reason is that if at time infinity y is not changing with time, then this derivative and this derivative are zero. So that's what we get. So of course there's always an assumption that y has reached a constant value at time infinity, so we just have to be careful about that. All right, we also saw that the behavior of the capacitors and inductors at 0 plus and at infinity is of great interest to us in analyzing circuits. So we saw that if there's a switching event or we have some initial condition, then we have to worry about how these devices operate, how they behave. We saw that if a capacitor has a zero initial condition before time zero, then from 0 minus to 0 plus, it acts as a short circuit because it wants to keep this voltage at zero. Similarly, an inductor starting with an initial condition of zero current acts as an open from 0 minus to 0 plus because it doesn't want any current to flow. At time infinity, on the other hand, if all of the values have reached a constant amount, all the voltages and currents, then the voltage on the capacitor is constant, there's no current through it, so it's an open circuit. The current through an inductor is constant, so there's no voltage across it, so it acts as a short circuit. We have to remember these four cases. All right, then we started by looking at this series RLC circuit with a step applied to it. So V1 U of t. We assume zero initial conditions in these two devices, and we would like to analyze the circuit. We can find this voltage or this current or this voltage, etc. Right? So there are many interesting parameters that we can find. Let's assume that V out is the quantity of interest to us, and we'll try to find the differential equation that expresses V out. So let's go ahead and find the step response. So I will draw the circuit again. So we have V1 U of t going into the circuit as a step. Then we have R1. Then we have L1. And then we have C1. All right, and what we're trying to find is this voltage V out. And it will be probably a second order differential equation. And we have two initial conditions, right? One is this voltage is zero, and one is this current is zero. So we just have to see how these play out in solving that differential equation. Okay, so because V out is of interest to me, I would like to express everything in terms of V out. So the voltage on the cap is V out. How much is the current through the cap? C dV out over dt, right? So this current is given by, so we'll say current through cap is C1 dV out over dt. The current with the direction I have chosen goes from high potential to low potential, so it takes a positive sign here. Now this current continues to flow from the inductor and the resistor. So I have a current going like this, right? It goes through the resistor, through the inductor, through the capacitor, it goes back to the voltage source. So how do I find the voltage across the inductor? The voltage across the inductor is L di over dt. So the voltage on the inductor, voltage on L1 is just L1 di over dt. And the current to the inductor is known, right? It's this one. This current flows through everything. So that would be C1 dV out over dt. And how do I choose the polarity of the voltage across L1? Because the current is going from left to right, and because I wrote this with a positive sign, I have to have high potential here and low potential here, right? Current goes from high potential to low potential if this sign is positive. And finally, the current through R1 is the same as the current through the cap, right? And the voltage across R1 is given by the following. So voltage on R1 is given by the current, which is C1 dV out over dt, times the resistance, R1 C1 dV out over dt. All right. Okay. How about the polarity of the voltage across R1? Because the current is going from left to right, and I have a positive sign here, I will have to pick plus here and minus here, from high potential to low potential. All right, so now we have all the voltages, we can write our KVL. You can see that this is very similar to what we did last time, except that last time we didn't have this voltage source here, right? Everything else was there, so we're doing the same thing. Okay, so let's go ahead and write our KVL. We're going to start from here. We say we go up the potential, so plus V1 U of t is, and then going down the potential, minus R1 C1 dV out over dt. We're going down the potential, so that's the voltage across the inductor, L1 C1 d squared V out over dt squared. And then finally the voltage across the cap, going from high potential to low potential. This should be negative, going from high potential to low potential, and then minus V out, and that goes back to the original point, so the result is 0. Okay, so that's our differential equation. As usual, we're going to keep all the terms, including V out, on one side, and then that input on the other side. So we have this form. We have L1 C1 d squared V out over dt squared plus R1 C1 dV out over dt plus V out is equal to V1 U of t. All right, that's the differential equation. Okay, and we have to solve this differential equation with two initial conditions. What are the initial conditions? Well, we know that V out at time 0 plus is 0. How do we know that? Because we decided that the capacitor voltage has to be 0. Our assumption was that the initial conditions are 0. And we decided that if the cap voltage is 0 before time 0, it's going to be 0 after time 0. It's like a short circuit. So that voltage has to be 0. What else do we know? Well, we know that the current through the inductor is also 0 at time 0 minus, and it has to be like that at time 0 plus, right? This looks like a short circuit, if you will. And from that perspective, I see that the current through the inductor is actually the same as the current through the capacitor. So I will say C1 dV out over dt. This is the current through the capacitor and through the inductor. At 0 plus has to be also 0, because the inductor doesn't like its current to jump. So now we have two initial conditions expressed in terms of V out. We have an equation for V out. We can solve everything easily. All right, so how do we go about solving this equation? What we have done in the past was when we had a 0 term on this side, and we said V out must have one of these three forms, right? Those three forms here. The question is, now that I have a step on this side, Can I just still use those equations, or do I have to make some change? So that's what we have to think about. Okay, so to do that, I think we should try to plot V out as a function of time just qualitatively to get a feel for what's going on before we go back and try to see what form we should choose for the solution. So let's go ahead and do that. That's always useful, right, to predict what the output should look like. Okay, so let's see what we can say about V out. V out as a function of time. All right. Okay, so we know a few things about V out. V out at time 0 minus and 0 plus is 0. That's what we decided because this cap doesn't want the voltage to change. So V out is like this. All right. Now the question is, what happens after this point? In particular, how much V out do I have at time infinity? That should be something I can predict without too much mathematical labor. And that is our quiz of the day, so I will give you 1 minute to think about it. All right, so how much is the final value of V out? Okay, so we have to go back to the circuit and understand. Of course, from the differential equation and based on what I showed you last time, based on this observation here, we can try to predict what the final value is. But from the circuit itself, we should also be able to predict that, right? So what can we say here? All right, well, we decided that at time infinity, the capacitor is an open circuit because its voltage is constant. That's what we are thinking, that's what we are hoping, and that means there's no current through it. So this is open. At time infinity, this inductor is a short circuit because we are thinking that its current will probably be constant, so LdI over dt will be 0. This voltage is 0, it's a short circuit. So let's try to draw the circuit, this whole thing, at time infinity and see what it looks like, right? So we say at t equals infinity, we have this guy, which is now constant, so I can just put a battery there. So here's a battery of value V1. I still have my resistor R1. The inductor is a short circuit because we are thinking that this current is constant, so its voltage is 0. And the capacitor is open, so it's no longer here. And that is the simplified circuit. So how much is V out here? Well, we see that because there's no current going anywhere, the voltage drop across R1 is also 0. And that means that this voltage is the same as this voltage, right? So because there's no current in the loop, the voltage here is 0. And this voltage is 0, this voltage is 0. If you write a KVL, you decide that this voltage has to be equal to this voltage. So we say V out at time infinity is V1. And that means that V out is going to grow and approach V1. Now, it could be a smooth growth, over-damped or critically damped, or it could be that it will go crazy for a while before it settles, and that's okay. But the point is that it has to get to V1 at time infinity. Okay, so that is the general shape that we expect for V out. 0 around 0, V1 at time infinity. And from just these two observations, we can decide whether these forms are good enough for what we want to do. Are they good enough? Suppose we have an overdamped system, something like this, right? Will this predict V out properly? Well, we know that in an overdamped system, S1 and S2 are negative, so the two exponentials die away. So at time infinity, this will not give us a value of V1. So we have a problem, right? So how do we do that? Okay, so what we will try to do is start with these solutions and then say, okay, well, we need a final value here, right? A final value that is not 0 anymore. So why don't we go and do this? Why don't we go and just add V1 right here? V1, V1, V1. So that's our guess that the solution to this system will be of this form. If we have an overdamped response or a critically damped response or an underdamped response. We know that in these RLC circuits, all of these exponentials will decay with time, right? They all go to 0. So in all three cases, the final value will be V1 if I just add V1 here. And the rest is just exponential decays with some oscillation or not, and that should satisfy our second order differential equation. So I'm following sort of a heuristic approach. I'm not actually solving this differential equation carefully, but our intuition and our background differential equations suggest that this is a proper approach to writing the solutions of the system. Now, if I were to find the final value from what I showed you before in terms of a general differential equation, we would see the same thing, right? So at time infinity, what's happening here? We have V1 here, and these derivatives are 0, so V out is just V1 over 1. So it's V1, and that makes sense. So that's what we decided that should happen. Okay, so from now on, for this particular circuit, with this step response, we will assume that the three responses look like this, and then proceed. V1 is known. That's the step of the height of the step. We still have to find A1 and A2. All right. So the values of S1 and S2 are of course known. The characteristic equation is always for the homogeneous part of the equation, meaning this side is set to 0, and the characteristic equation is the same as before. So we see that the characteristic equation, if I divide by L1 C1 to make it easier to see, is S squared plus, so C1 goes away, we have R1 over L1 S plus we have 1 over L1 C1, and that's 0. You can see that this characteristic equation, of course, is the same as what we had for the natural response. So the two roots of this will follow everything we said for the natural response, right? Depending on what the value of R1 is with respect to 1/2 of square root of L1 over C1. Okay, so with all of these, now we are ready to take each case and try to find the complete solution. All right, so let's go ahead and do that. So we say case 1. We have an overdamped response, and if you remember, for the series RLC combination, that requires that R1 be large enough. This resistor has to be large enough to kill any possibility of oscillation here. So R1 has to be greater than 1/2 of square root of L1 over C1. If that condition holds, the solution is of this form. So I can say that V out is equal to A1 e to the S1t plus A2 e to the S2t plus V0. Does this take a U of t? Yes, because it's 0 before time 0. So to be precise, we multiply this by u of t. We just need to find a1 and a2, right? Okay, how do I go about doing that? Well, I have two initial conditions, right? So I just have to satisfy these. Let's go ahead and do that. At 0 plus, V out should be 0. So we just plug in t equals 0 here. Let's change the color to maybe this one here. Okay, so what we know is that A1 plus A2 plus V0 at time 0 should be equal to 0. Okay, how about this one? The derivative has to be 0 at 0 plus. The derivative would consist of A1 S1 plus A2 S2. If there was this 0, this whole thing has to be equal to 0. All right? What happened to, we say derivative of this guy times this, derivative of this guy times that, right? So we have delta of t times this. As usual, you have to convince yourself that delta of t times this is 0, has a 0 weight, has a 0 area. And that makes sense because what is left, what is multiplied by delta of t is actually the value of V out at time 0. Right? You can see this, right? It will be delta of t times this evaluated at time 0, and that would be just V out itself at time 0. So the weight of the impulse is 0. We don't have to worry about that. So from these two conditions, we can find A1 and A2, and then we have the complete solution for the system. In this case, because it's an underdamped response, the output just goes up and slowly approaches its final value. Okay, how about, let's see, there's one interesting point that I wanted to mention here. This is just a point of curiosity. You see this V out here, starts from here, and does it go up like this, or does it go up like this? Which one of these should we expect for V out? The difference is what? The difference is the derivative of V out in this vicinity. This derivative jumps, it's 0, and then suddenly jumps to a certain value. Like a simple RC circuit, the first order RC circuit, that's what happens. Is 0 and the derivative jumps. But the red waveform has a derivative that doesn't jump. The derivative is 0 here, even 0 at 0 plus. So which one of these is the correct waveform? So we have to go back and examine the derivative of V out. And we have that. The derivative of V out is 0 at 0 plus. So the correct waveform is indeed the red waveform, not the purple waveform. Okay? So we say, since dV out over dt at 0 plus is 0, say V out takes off slowly, right? V off takes off, V off starts changing slowly. So here it changed quickly, but here, because the derivative has to stay at 0, it only smoothly and gradually tries to increase. So that's a property of second order systems. We did not have that property in first order systems. Okay, all right, so that's the situation that we have in this case. Let's go to case number 2 and see what we have when we have a critically damped response. So our guess again is this. So we say V out of t is equal to, again, we're going to have a step, right? So it will be A1 e to the S1t plus A2t e to the S1t plus V0 times u of t. Okay, so that is the response we expect. And again, how do we find A1 and A2? Same story. We have to have this condition and this condition, right? So you say A1, so at time 0 plus, this is 0, you have A1 plus V0. So A1 plus V0, that should be 0. And then the derivative also should be 0. Taking the derivative of this gives us A1 S1. Then we have the derivative of t times this, so that would be plus A2. And the other one goes to 0, this one goes to 0. That has to be 0. So from these two we can find A1 and A2. Okay, what does the waveform look like? The waveform actually looks like this red one, except that it's a little faster. So just for comparative purposes, we'll try to plot it like this. So V out as a function of time. So let's change the color to maybe green. So we still have a 0 slope here. It takes off slowly and settles to V1. So that's the case of critically damped response. And the case of overdamped response looks like this. So that's the only difference between the two. Okay, so this is overdamped, and the green one, I'll use green here. The green one is critically damped. All right. So by properly choosing R1, so again, it's the same situation here. So in this case, we have R1 is equal to 1/2 of square root of L1 over C1. So we have managed to speed up the response without any oscillation, without any overshoot and undershoot. Okay, and finally we have case 3 where we have an underdamped response because R1 is too small. If R1 is really, really small, the circuit approaches an ideal LC circuit and it tends to ring for a while. So we say case 3. Let's change the color here. So we say case 3. So we have underdamped response, and we have to use this equation here. So we say V out is equal to A1 e to the alpha t cosine of omega 1t plus A2 e to the alpha t sine of omega 1t plus V0. We still take a u of t, right? So this whole thing has to multiply by u of t. All right, and alpha and gamma 1, omega 1 are known, right? So again, if based on the equations that we have here, if we write S12 as minus R1 over 2L1 plus minus 1/2 J, so I have to swap the two terms under the square root. So the first one will be this one, 4 over L1 C1 minus this one squared, so R1 squared over L1 squared. This is what I've done in the past to find alpha and omega 1. So in this equation, then alpha is known to be this one here, and then omega 1, the frequency of ringing approximately will be this one here. So that's omega 1. Okay, we just need to find A1 and A2. So we have to enforce the initial conditions, right? So I'll leave that as an exercise for you. You have to take this derivative carefully. First, we replace t with 0 for this condition. So that's just A1 plus V0 is equal to 0. Then we take the derivative of this whole thing, evaluate at time 0, and equate to 0. From those, we can find A1 and A2. All right, the underdamped response looks like this. I'll just try to put it over here. So it will try to go faster. So let's change to black here. So it tries to go faster, but it's going too fast. So it will ring before it settles. All right, so that is the underdamped response. Okay, all right, so we have these three cases. You can see that the overall result is very similar to what we did for the natural response, except that here V1, this voltage across this capacitor, ends up not being zero, because as we analyzed, we saw that the final value has to be equal to the step value. So for that, we have to have this term here, but the rest of the calculations are very similar. Of course, A1 and A2 in this case, in these three cases, are not the same as A1 and A2 computed in the natural response, right? Because here we have different equations. Here we have A1 plus A2 plus V0 equals to 0. Okay. All right. So just to have some appreciation about these three responses in a second-order system, and generally in systems that have the possibility of approaching their final value slowly, approaching their final value optimally, or approaching their final value with some fluctuations, some oscillations, we need to have some analogy to see why one response might be preferable over the other two. So let me give you a simple analogy here. So we say robotics analogy. Second-order differential equations govern many different systems, not just basic circuits, even social systems and mechanical systems, biological systems. So here's an example of sort of a mechanical system used in robots. And I want to show you what it means to have an overdamped response or a critically damped response or an underdamped response. All right? So here's how it goes. Suppose I have a robotic arm, that has to pick up eggs and place them in containers. And has to do this many, many times during a day. Probably some thousands of eggs per hour, right? Okay, so let's draw a little robotic arm. We'll try to draw it like this. Okay, so these are the two fingers of the robotic arm. They have to go and grab an egg, move it from here to here. All right, so we'll call the distance between these two fingers something. Let's call it, for example, capital D. Okay, all right, so obviously the two fingers begin from a large D, and they approach an egg. And then once they approach the egg, D decreases until the fingers grasp the egg. Right? Okay. So D starts from some final value and comes down to this value. So let's try to plot D as a function of time. So D as a function of time starts with some larger value. So let's say D1, and if the diameter of an egg is called D2, it wants to come down to D2. So this is D2. So it is possible that these two fingers begin from D1 and very quickly want to reach D2. Remember, because the robot is doing this many, many times, we want this to be pretty fast. So how would that work? So we can have three responses here for this robotic arm. It could be that the response is overdamped. So it goes from D1 to D2 very slowly, goes like this. So that's a conservative solution, meaning that we want to make sure that it comes down slowly and it touches the egg and then grabs the eggs and puts it over here. So that would be an overdamped response. What's the disadvantage? Well, it takes too long, so we can't process that many eggs per day. Now, how about a critically damped response? A critically damped response allows D to go from D1 to D2 in optimal time. So it will be something like this. It starts from here and quickly approaches D1. So this is critically damped. All right? Okay. How about an underdamped response? Would that be acceptable? An underdamped response means that we start from here, and this is the egg, right? Instead of reaching this diameter, the robotic arm wants to go like this, to even less than the diameter of the egg. So it wants to go like this. So let's change the color to green. It wants to go like this. Is that acceptable? No, because that's going to crack the egg, right? Because here, the distance between these fingers is less than the diameter of the egg. So when it goes down, it's going to crush the egg. So we see that we must make sure we never get to an underdamped response, because that would be disastrous. We can go with a critically damped response, because that would give us the shortest amount of time for the two fingers to grab the egg. So they will allow us to maximize the number of times the robotic arm can do this. But of course, we have to be careful, because with the slightest change in the values of the system, we might go from critically damped to underdamped, right? So we have to be careful. So we may want to be a little conservative and choose something between these two. And you can see that in many different systems, right? The tendency, if we are not controlling things very well, and we are aggressively trying to get to our final value, we actually fluctuate, right? We go to the other extreme, then come back to the extreme, and so on. So that's a nice example of how these responses play a role in many of the things that we build and we use every day. All right. Let's see. Okay, now that we have studied the step response of the series RLC circuit, we can try to look at this impulse response and see how that can be obtained. The impulse response can be obtained one of two ways. So let me try to write here. Impulse response of series RLC circuit. Okay, how do I do that? Well, approach number one. So approach one, we know that if we have the step response to a system, we can find the impulse response. How do we do that? By taking the derivative of the step response. So here's how it goes. If we have a step to a system, so here's some system, right? And it gives us some sort of response. For example, this. So let's call this y of t. And now instead of a step, I give an impulse to the system. Here's an impulse to the same system. Then all I need to do is take the derivative of this with respect to time. That will be the impulse response. So this would be dy over dt. Why does this make sense? Well, because for the input, I have taken the derivative with respect to time when I go from step to impulse, right? The impulse is the derivative of the step. So it should, the same thing should happen at the output, because it's a linear time invariant system. So here also the response should be differentiated to find the output corresponding to an impulse input. So we can always do that. We have found the step response. We have one example here, this equation down here. We have another equation here, and find another equation here. So we have to go and very carefully take the derivative of these responses with respect to time, and that will give us the impulse response of the system. All right, so that's one approach. But there's another approach that is more intuitive and still a little trickier. So there we have to think about the circuit very carefully and understand. So let me show you. So we say approach 2. So approach 2 says, okay, well, just let's draw the circuit and apply an impulse and see what it looks like, right? So here's our impulse. We say delta of t, right? It's a voltage that is 0 before time 0, goes to infinity and comes back, and then stays at 0, right? So that's delta of t. And we have R1 here, we have L1 here, we have C1 here. And now we would like to analyze the circuit in response to this impulse. Okay? And again, let's suppose that the quantity of interest to me is this voltage, although other quantities may also be interesting to look at. All right, so this becomes an interesting and very tricky problem if you want to do it intuitively, right, without going to the first approach. So how do I do that? Well, the point is that this voltage jumps to infinity briefly, and we have to see what else here can change. Because we have an infinite voltage, we might expect that the capacitor or the inductor may have a sudden change in their quantities, right? We said a capacitor cannot jump its current, cannot jump its voltage if the current available is not infinity. An inductor cannot jump its voltage an inductor cannot jump its current if the voltage available to the inductor is not infinity. But here, we have an infinite voltage briefly, and we have to ask ourselves exactly what can change in this inductor or in this capacitor. All right? So in other words, from 0 minus to 0 plus, exactly what happens? Does the out jump, or does the current through the inductor jump? Right? One of these two may be able to jump because we have an infinite voltage available. All right, so let's take it step by step and think about that carefully. So we say, can the current through L1 jump? So in other words, here's the situation. So let's say this current here, IL1. So IL1 is assumed to be 0 before time 0. And what we're wondering about is whether we can have something like this, right? Now it could be this way or it could be this way, really, but the point is there a jump in the current at time 0, from 0 minus to 0 plus? Okay. Well, it seems that there can be, right? Because if the current through the inductor jumps by some amount, so let's say it jumps to I1 here, then that means that this current is now equal to I1 at time 0 plus. That means that this current is equal to I1 at 0 plus. And that means that this voltage here is I1 times R1 at 0 plus. Is that okay? I'm writing all of these things down because we have to make sure that every device satisfies the equations that we have. All right, so how about the capacitor? The capacitor would want to have an infinite current to jump its voltage. Do we have an infinite current available? No, because the best we can hope for is that the current of the inductor jumps by some amount, but the current of the inductor cannot jump to infinity, because all we have for it is an infinite voltage briefly, right? So we say because the current of the inductor only jumps but does not go to infinity. So we say IL1 does not go to infinity, so V out cannot jump. Okay, so V out cannot jump. So let's see what has happened. This guy has a little bit of voltage, I1, R1. This guy has no voltage. How much is the voltage across the inductor during this transition when we apply this impulse? The voltage is indeed infinity, because this is infinite, this is not infinite, and this is 0, so the voltage across the inductor is infinite, and indeed the current through the inductor can jump. So we say since delta of t jumps to infinity, but the resistor and capacitor voltages do not, right? Decided that this voltage jumps to infinity, this voltage doesn't, and this voltage doesn't. So the voltage across the inductor does a jump to infinity. The voltage across L1 does go to infinity, so IL1 can jump. So you see what happened here? We made an assumption and we verified the assumption, and that shows that the voltage can jump. I will see you next time.